Hello, there's a new entrance exam Wiskunde B Maths B coming up soon. So in this video I will go over the preparation for that. First of all, the information about this can be found on this website. No graphic calculator is allowed, but a standard calculator is fine. Like a calculator with the functions of an exponentials, say you want to calculate e squared, or logarithms like the log of 2, or some trigonometric functions like cosine or sine. Take a pen and pencil. The pen can be used to answer the questions, either blue or black. You cannot use a red pen. Pencil you can use for making graphs if required. And don't forget spare batteries for your calculator. And take a watch to control time, since you can't use your smartphone. So the next pages of this is an elaboration of the program, of what you need to know. The first topic is the standard functions. You need to be familiar with all of these. So the power function, in which x is taken to some power n, exponential functions where x is the exponent, and then the inverse of these are the logarithms with base g, with this base cannot be 0 or negative, or not equal to 1, since 1 to any power is just trivially 1. Then the natural logarithm, and then the set of trigonometric functions, your sines and cosines, and the absolute value function defined here. This absolute value function can look simple, but it can be a little bit tricky. So let's say you often will see functions like a combination of a absolute value and another standard function like this. But this is just equal to the log x. But now when log x is greater or equal to 0, and minus log x when the log x is smaller than 0. So now you need to figure out exactly what the sign is of log x before you can apply either the plus sign here or the negative sign here. Then you can combine functions like this. This is a combination of 5 power function, where this constant 1 is just considered a trivial power function with n equal to 0. Then you can just multiply and divide these functions. You can also compose functions, where an example is given here. You need to be familiar with that. And the inverse of a function, you need to know how to obtain these. And let's say your y is f of x, then the inverse can be found by isolating x. So writing x as an expression in y, and that is your inverse function working on y. And say one example is given here. Y is equal to g to the power x. So how to isolate x and find this inverse? Well, take the logarithm with base g on both sides. So you get g log y equals g log of g to the power x. But this, of course, is just equal to x. So by doing this, we have isolated x and wrote x as in a form with y. So we conclude that the inverse function then at y is g log y. So next, page 5 is about domain and range. and also the interval notation. And the interval notation is like this. The square brackets means that the limits are included, and angle brackets like A, B, like this, means that they're not included. And when infinity is involved, then you use these angle brackets. So you could have some interval like this. And the rest is the powers. And the main rule here is a to the power m times a to the power n is a to the power m plus n. And most of the other rules follow from that. Page 6 goes into more details on the power functions. So we have the simplest one is just a constant horizontal line, which is when n equals to 0. Then you have a linear functions, a line, ax plus b, if a is the slope and b is the y-intercept. And then you have quadratic functions with a highest power of 2, so ax squared plus bx plus c. And if a is positive, the graph is opening upwards, and if a is negative, it will open downwards. And the number of intersections with the x-axis here is determined by a quantity called a discriminant, which can be calculated from these coefficients here. When the discriminant is positive, then there are two intersections with the x-axis. So these two situations, when d is negative, there are no intersections. These are this situation and this situation. And when the discriminant is 0, you exactly have only one intersection like given here. Then you can have root functions when n is 1/2 or 1/3. And these, say the square root is the inverse function of x squared, and the function is given here. It's only defined when for positive x, and the range is also positive. And for the cube root, which is the inverse of the cube, the domain is actually all real numbers, and the range as well, and that's given here. Then we have the exponential functions, where x is the exponent, and you can distinguish two situations. When a is greater than 1, then it's a convex increasing function with horizontal asymptote for x goes to minus infinity. So you can see here, x goes to minus infinity, this approaches 0. And for a between 0 and 1, it's a convex decreasing function with a horizontal asymptote when x goes to infinity. Just one note here on convex. How can you see that this function is convex? Well, I think the best way is to use that. Let's say I take two arbitrary points on this function, and I draw a line through these points. Then in the line segment between these points, you can see that the line segment is on top of the function. That means it's convex. And it's actually the same. This is convex decreasing. It's the same here. So the line segment will be on top. And for a concave function, say something that looks like this, the line segment will be below the function. That would be a concave situation. So that's also good to know for this. Then finally, this exponential function are used for an exponential growth formula. if you have exponential growth with a initial value b, then and a growth factor g, then the function looks b times g to the power t. And obviously b is the initial value, since when I substitute t equals to 0, the function n here is equal to b. Next is more details about the logarithmic function. As we saw from the example earlier, that the g log of x is actually the inverse of g to the power x. And here are some basic properties. The domain is all positive values of x, and it has a vertical asymptote when x goes from above to 0. And for g greater than 1, the graph is concave and increasing. And here they state that from 0 to 1 the graph is convex and decreasing, but decreasing, that's actually not correct. I don't know why they say that. It's actually it's increasing everywhere as well as concave. And I can take to any points here, then the segment here is below the function. And another way is actually to look at the second derivative. So anyway, I think this is incorrect. Then you need to know about all these basic calculation rules for logarithms. And one particular one is how to change the base of a logarithm. Say you have a logarithm of base 5 of 25, then not that it's very smart, but you could write it as the natural logarithm of 25 divided by the natural logarithm of 5, the base. And both of these actually is equal to 2. Then trigonometric functions, the sine, cosine, and tangent, how they're defined in a right angle triangle. You need to know about the unit circle, and here is an example for the cosine. If you look at an angle of 30 degrees, then the cosine is the projection of this point on the x-axis, which is 1/2 square root of 3. And then if I go 45 degrees, you end up here is 1/2 square root of 2. And 60 degrees end up at exactly 1/2. And these the same for the sine, which will be the projection on the y-axis. And this is best to all remember. If in case you forget, since you can use a kind of simple calculator, so let's say I forgot what the sine of 30 is, I can just go to my calculator and enter the sine of 30, I find 0.5, or say the sine of 45, I find 0.707, which I recognize as the 1/2 square root of 2. You also need to be able to convert degrees in radians and vice versa. So the sine and cosine function have certain minima and maxima, and they can be easily found from the unit circle as well. Let's look at this. The sine is the projection on the y-axis. So when is that a minimum? Well, here on the circle. And when do you reach that? Well, you need to rotate here by a minus 1/2 pi. And then you can add, say, a integer number of 2 pi to it. So that's this here. And for the cosine, the projection is on the x-axis, so the minimum is here, and that can be reached by a rotation of pi here. So you get pi, and then again you can add an integer number of full rotations, 2 pi. And the same you can do for the maxima. It's just here for the cosine here on the other side and for the sine here on top. Now for the zeros of these, you can see that there are actually two zeros for each sine and cosine. So let me, here for the cosine, when is the cosine zero? Well, cosine is the projection on the x-axis, so the zeros are here, and that's a rotation here of half pi. And rotation, and then if you go a pi further, so plus pi, then you also end up in zero. So you get 1/2 pi plus k pi. You can repeat this. And you can do the same for the sine, and the sine is zero here at zero rotation, or have an integer number of pi's. So the shape is a sinusoid, and there are also these symmetry relations which you all can again easily see from the unit circle, the best. So say I take a point here, say with rotation x, then actually the projection on the y-axis is the same from when I'm in this point, which is rotation of, well, pi minus x. So this will be pi minus x. So yeah, these symmetry relations are also useful to know, or at least how you can derive them. Then horizontal translations. If you take the sine function, which is here in the red color, if I translate it horizontally by 1/2 pi, if I translate it to the left, so by minus 1/2 pi, then I get the cosine back. So a translation to the left by 1/2 pi means that you need to add 1/2 pi to the function. So the cosine of x is basically sine x plus 1/2 pi. Then they give here the general form of a sinusoid, and from the parameters there you can find the equilibrium, the amplitude, and the period. And the simple harmonic motion is a special case of this. Let's just take as an example, let's say this function given here, and the amplitude is the absolute value of the coefficient in front of the sine. So absolute value of -8 is 8. The period can be found from this equation here. So 2 equals 2 pi over the period t, from which you find that the period must be 1 over pi. And the equilibrium is at y is equal to 3. Now the core topic of the exam is really differentiation and integration. So you need to know the derivative of these standard functions here. And you need to know how to differentiate combinations of functions, like the sum rule, the product rule, the quotient rule, and the chain rule. For sure you get many questions about this. Then you need to know definition of the antiderivative, or also called the primitive. And so function capital F is an antiderivative of f if the derivative of capital F is the function f itself. And you can always add an arbitrary constant. Adding an arbitrary constant, that function, resulting function, is also an antiderivative of f. Then you need to know the definite integral. That's the integral between two fixed points of a function, and that's given by the difference of the antiderivatives in the extreme points in the interval. And the other part is how this relates to area. If a function in an interval a to b is strictly positive, then the area of the region bounded by the line x equals to a and x equal to b is equal to the integral of a to b fx dx, and that's given here. The standard antiderivatives that you need to know are all given here, so go over this. Then you need to know the rules for combinations of functions and to find the primitives, including kind of a simple chain rule that tells you that of functions of this form, ax plus b, of f of ax plus b, the primitive is given by this form here, and it's something you can easily show by using the chain rule for differentiation. So if I take the derivative of this function capital G given here, you can stop the video and just follow this. If I take this derivative, I get the original function, the g of x back. So I've proven that this function here is the antiderivative of the function here. And one example would be, say I have the function sine of 3x minus 5. And the antiderivative of this is simply 1/3 times the cosine 3x minus 5. Then a definite integral is given here. You can be split up into two intervals if this c here is between a and b. I think that's pretty obvious. And an often asked question is about the area of a region with an upper boundary and a lower boundary, given by two functions f and g. And that's that definite integral is given here. So the area between f and g, if f is always if f is an upper boundary and g a lower boundary, is given here. Another often asked question are these volumes of rotation along either the x-axis or the y-axis. And the x-axis is a little bit more straightforward. You just need to do the integral from a to b, the starting point and the end point of the function squared, multiplied by pi. For rotations around the y-axis, it's a little bit more complicated. It's given here. You need to find actually the inverse. So you need to again express x into y and then substitute it in this equation. And I have an example of that here. If I have a function minus x squared plus 4 and I want to know the volume if I rotate it around x, the y-axis, between x is equal to 1 and x is equal to 3, what I need to do is find the antiderivative of this function, and I do that by again isolating x. So y is minus x squared plus 4, so x squared is 4 minus y, or x is the square root of 4 minus y. And then I just plug this in, I get this integral over y, and then I find the answer. So if you don't understand this well, just stop the video and just follow the math here. The last point I don't think is very important. Moving to geometry. First about straight lines. So this here is a general form of a straight line, which you can easily write as in this more commonly used form: y is ax plus b, except if the line is vertical. Now, in this form, a is the slope of the line, and the slope is the increase in y you get for an increase in x. Then the direction angle of a straight line is the angle between the line and the x-axis. And the tangent of that angle is equal to the slope. So that's, in this case, I have this line here, and alpha here is the angle with the x-axis, and the tangent of this is the slope. And if I have two straight lines, then the angle between them is the smallest angle. So if I have this green line and this red line, the angle between them is actually defined as the angle here, so which is the smaller angle. And they make a remark here: this angle is determined by drawing both lines in the Cartesian plane and indicating the direction angles at the intersection. I'm not entirely sure what they mean, but let's look at this example. The red line has a direction angle alpha 1, and the green line a direction angle alpha 2. Then in order to actually find the smallest angle, you need to actually look at the angle in this direction, which is 180 minus alpha 2, and then subtract alpha 1. So you just need to make a drawing of the situation and then just take the proper angles. So if they are perpendicular, then the product of their slopes equals -1. Perpendicular line and distance. The slope of the line perpendicular to the line with equation y ax plus b is equal to -1 over a. And that's because -1 over a times a is equal to -1. And that was the condition to be perpendicular. So the distance between 2 points is given here. That's just Pythagoras. The projection of a point on a line is given here. Say you have a point P and a line L. Then to find the projection P prime, you need to find the line K, which is perpendicular to L and goes through P. So by using this rule, you can find the slope of line K and then just demand that it goes through P. And then you can find the equation for K. And then you find the intersection of K and the line L, and that intersection point is P prime. Then the distance between this point P and the line is just given by the distance of this segment here. And they say there is some equation for it, but you don't need to memorize that. But what you will do if they ask for it is just finding P prime and then use the equation here to find the distance. So they state we need to know what a line segment bisector is. Say I have a segment AB and the line segment bisector consists of all points P for which the distance from P to A is the same as the distance from P to B. So it will look like a line like this, and every point P is at the same distance from A and B. So it basically splits this segment in half. And the same, you can have an angle bisector of two lines L and M, and these bisectors are all the points P which are in have the same distance from line M and line L. And as we saw above, this distance is measured by the perpendicular projections on these two lines. Next, geometry in triangles. We need to know Pythagoras, the area of a triangle, the sum of the angles should be 180, and the law of the sines and the law of the cosines. And the law of the sines says if I have a triangle with sides A, B and C and opposite angles alpha, beta and gamma, then this relation holds. So all the opposite sides divided by the sine of the angles are equal. And they also happen to be equal to 2 times the radius of this circle called the circumcircle. And the laws of the cosine says that if I take the cosine of one of the angles, then the opposite segment C squared is equal to the sum of the other segment squared, then minus 2AB times the cosine of this angle. And actually this holds for all angles, but I only wrote the version for the cosine of gamma. But it holds also for, say, the cosine of beta, and then you need to replace C by B, etc. A isosceles triangle is a triangle with 2 equal sides, 2 legs that are equal in length. And they also have a property that the opposite angles here and here are the same. And if all sides of a triangle are the same, then, which is not the case in the one I drawn here, then it's called an equilateral triangle. And in that case, all the angles here are 60 degrees. Okay. And I actually have seen a question, that's why I also add this to the video, that you have to prove that a certain triangle is equilateral. So definitely something you need to know. When are 2 triangles similar? They're similar if the angles of both triangles are equal. And in that case, also the ratio of the lengths of the sides are equal. So they're all sides of similar triangles have the same length ratio. The medians are the lines that go from a vertex to the middle of the opposite line segments. So there are 3 of them, and they meet together in called a centroid. And so apparently that is something they ask you to know about. And the centroid actually divides the median in 2 parts, and the length of the longer part is twice the length of the shorter. So the length of this is twice that of this one, etc. So this is twice that of this one, this is twice that of this one. So then you need to know some basic things about vectors, 2-dimensional. It's a translation over a certain distance and in a certain direction. So it has a certain length, which you can indicate by the absolute value across the vector. And a vector that indicates a translation from, say, a point A to a point B, you can just denote as AB with an arrow sign on top. So that will be this vector. This is its length, and this is the direction, say northeast or a certain angle. And you can add vectors. So if I have, by the head-tail method, if I have a vector A here in red and B in green, I can add them by just putting the tail of B on the head of A and find what that resulting factor A plus B is in cyan color here. Obviously you can put a factor into coordinates. You can add them by component. You can multiply them by a scalar. You can define the length by a factor using Pythagoras. And you can also decompose it along the axis. So say I have a factor A here, then this is actually the sum of factor A in the x direction and a y in the y direction. These are the components of the factor. Then for factors you can define the inner product, which is given if you write the factor into components as just the sum of the products of the different components. So this you definitely have to remember, as well as the equation for the inner product. In particular, since this can be easily used to find the angle between two factors. If I know the inner product, I just divide by the norms, then I can find the cosine of the angle. And in particular, if two factors are perpendicular, means the alpha is 90 and the cosine of 90 is 0, so the inner product is 0. So if two factors are perpendicular, their inner product is 0 and vice versa. This is pretty important. Now, for a line, we have seen a representation in the form y is ax plus b, but you can also write it in a vector representation, and it works as follows. You have a position vector AB and a direction vector PQ. And if I just take an arbitrary example, say I have a position vector here, which I call P, and a direction vector D here, so it's roughly in the southeast direction. Then I can look at all the points I get by adding some constant scalar lambda times this vector and add it to the position vector. And then I get the resulting line here. These are all the points I get by doing this. So basically that forms a line. Again, a position vector and a direction vector. And a normal of a line is a vector perpendicular to the direction vector. So let's say I want to find a normal. Normal means a line perpendicular to this line. I just need to find a direction vector that's perpendicular to this direction vector. And if it's PQ, then a vector Q minus P is actually perpendicular to this direction vector. Why? Well, the inner product of P and Q minus P is 0. So, drawn it here in yellow, this is indeed like a perpendicular vector. And this kind of thing can be used to find a line perpendicular to a certain line. Circles. So you need to know what the equation is of a circle with a radius r and center point AB. I've seen quite a few questions about this, so definitely a must-have. You need to be able to compute the intersection with a straight line. So as drawn here, a straight line will potentially intersect at 2 points, and it's just a matter of solving two equations with two unknowns. So the first equation is that of the circle and the second one that of the line, and just substitute the equation of the line into the circle, and you get a quadratic equation that you know how to solve, and by that you will be able to find the coordinates of these 2 points. Then the tangent line, you need to know what that is. It's drawn here. It's a line that's perpendicular to the radius at that point. So if you, for example, want to calculate the tangent, the expression of the line through a certain point, then you first calculate the radius, and then you, either by this rule for the slopes of perpendicular lines or the vector representation, find out what the direction is of this tangent line, substitute the point here, then you find the expression of this line. Then you can compute intersections of circles. You do that by, you basically have 2 equations similar like this, and then x squared plus y squared can always be eliminated by subtracting them. Touching circles are lines with a common tangent lines. Tangent lines through a point P outside the circle. The points of tangency both have the same distance to P. So if I would draw another tangent line here that goes through a point P, then it will have the same distance to the points. So these points of tangency here have the same distance to P. If you want to compute the distance between 2 circles, it's drawn like here. You just need to draw the line through the centers of the circle, and then the length of this line segment is the distance. And to compute, say I have a line in a circle, and I want to calculate the distance, then I need to find the perpendicular line, the line perpendicular to the line that goes through the center, and then intersect it with the circle here, and then calculate the distance here. Triangles and circles. So a circumscribed circle of a triangle is a circle that passes through the 3 vertices, and the center of that intersection is the intersection of the line segment bisectors of the sides. So let's go back to, we saw that a little bit before when going through the sine law. Here it is. So this is the circumscribed circle, also called circumcircle, and the bisectors of the line bisectors, the line segment bisectors probably, will cross in a point. So let me draw the one of segment B here, and the one of segment C. So again, it's perpendicular, splitting these segments into 2. It's a little bit messy, but I think you get the point. So now I do it for segment A. So they all cross here in the center of the circumcircle. That's what I'm stating here, and apparently something that you need to know. Okay. Then the inscribed circle of a triangle has all 3 sides as tangent lines. So here I have a arbitrary triangle and the inscribed circle. Then this center point is actually the intersection of the angle bisectors. So bisectors of the angles. So different from the center of the circumscribed circle, where we're talking about line segment bisectors. Okay. Then Thales or theorem says that if you have a triangle and a circumscribed circle, if it happens to be that one segment of the triangle is a diameter, like shown here, meaning it goes through the center, then the opposite angle is 90 degrees. And vice versa, it is also true. The next page is about drawing and sketching graphs, so you just need to look at the key point, like the asymptotes, the shape, the minima, the maxima. Then about transformations, you need to know about horizontal translations, vertical translations, multiplication, vertical, horizontally, and a vertical multiplication, and reflection in the y-axis, which is basically flipping x, and reflection in the x-axis, which is flipping the sign of y. And then you need to look at line symmetry in the y-axis. Basically that means it is symmetric under reflection in the y-axis. So that will be an even function. And then you can look at point symmetry in the origin. It's point symmetric if f evaluated at minus x is equal to minus f evaluated at x. So an example of that would be this function. Let's say I evaluate here at minus 1, then I see that it's actually the opposite sign of the evaluation at 1. So it's kind of a symmetric under reflection in this line y equals to x. And finally, the vertical distance between two graphs, two function f and g, with a vertical line x equal to p, is f evaluated at p minus g evaluated at p, but then the absolute value, so which is indicated here. Finally, an important topic are limits. You need to be able to compute limits, and you need to able to tell if a function has a horizontal asymptote or a vertical asymptote by evaluating limits. A particular example would be a function f(x) divided by gx, where gx is equal to 0, but f(x) is not equal to 0. This one, according to this rule, will have a vertical asymptote. And another possibility is that a function has an oblique asymptote. That means if you take the limit of the function minus the expression of a line and find that this goes to 0, then it has an oblique asymptote. The same for if x goes to minus infinity. So this you need to remember. About limits, I a little bit surprised L'Hopital is not mentioned, but that's required for certain situations, such as sine x over x. And roughly it will say that if the both f and g in a quotient function like this goes to 0 or to plus or minus infinity, then the limit is just given by the limit of the derivatives. So in this case, sine of x divided by x can be evaluated as cosine x divided by 1, which goes to 1. Or say a function e to the power x divided by x, in which case both f and g go to infinity. You can apply it as well and find that it is e to the power x divided by 1, which is infinity. And there are some conditions which apply, but generally for this level, I don't think they will have situations that these conditions do not apply. But basically it says that the derivative of g has to be non-zero in an interval around the point, which although it can be 0 in the point itself. But for example, in these cases where g of x is just x, that's easy to show. Then finally, a perforation. What is that? That means that say we have a function for which f in a does not exist. But if the limit from x approaching from below is the same as the limit of x approaching from above, and if they're equal, then we have a perforation. Basically, in discontinuity that can be removed. So you have to prove that these limits are the same. And when these limits are actually different, then you have a jump discontinuity. Next, page 18 is applications of the derivative. So still a little bit calculus related. So f prime at a point A is the slope of the tangent line of graph f in point A and FA. And we learned already earlier a little bit about what the slope is. So the angle between two curves in a point P can be found from finding the angles of the tangent in this point P. So from both curves just calculate the derivative and find what the slopes are. So the derivative, the sign of the derivative will tell you if a graph is increasing or decreasing. And when the derivative is 0, we can have a minimum or a maximum. Actually, the way to say it is, in a minimum or maximum we have f prime of x is 0. F prime of x is 0 doesn't necessarily mean a minimum or a maximum, and this would be a situation in this point here. F prime of x is 0, you have a horizontal slope, but the function doesn't have an extreme. So what you have to do, if they ask you about extremes, then you have to solve f prime of x is 0, and then by sketching or other way you have to figure out whether or not indeed it is an extreme. And you can do this by looking at the value of the function a little bit to the left and the right. Vertices. I'm not sure if that's important. Yeah, you have often questions about graphs touching. And what does that mean? It means that if two functions f and g touch, they will intersect. So f of x is g of x, and their derivatives are the same. If they're perpendicular at their intersection, they intersect, but the product of their derivatives is equal to -1. You've learned before that if the product of slopes is equal to -1, the two lines are perpendicular. Now, if the derivative function has an extreme, the graph has a point of inflection. And so what does that mean? Well, derivative has an extreme. For sure, the f double prime, the second derivative has to be 0. And as discussed above, it doesn't, if this is the case, it doesn't necessarily mean it's an extreme. So again, you have to check that at this point, indeed, the derivative function has an extreme. Although they state here that from the wording of the question, it's usually already clear. For example, if they state this function has one inflection point, and if your calculation shows, for example, by solving this, that there's one inflection point, you know that it's actually an extreme. Then, so we already know the sign of the derivative tells you if the function is increasing or not. And then on top, the sign of the second derivative will tell you if it's convex or concave. And earlier on, I already explained what convex and concave means. Questions about parametric equations are often asked. They describe paths in space. They consist of a point of which the x coordinate and the y coordinate depend on a parameter t. And you can have vertices, or I guess extremes. You have a horizontal tangent when y prime of t equals to 0, like given here for the example of a circle, and a vertical tangent when x prime of t is 0, like given here. If both x and y are linear in t, then this describes a straight line. You can actually write it in this way, which looks exactly like the vector representation of the line we saw before. If the path looks like this, then this describes a circle with center AB and radius r, and you can easily check that it satisfies this equation here. Now, if both x and y are periodic functions, then the period of the total movement of point P is the least common multiple of the periods of x and y. And remember that the periods can be found from the coefficient in front of well, t in case of this parametric function. So from this you can find the period of x and both of y, and then you just need to take the least common multiple of these two periods. And you can define a velocity vector as x prime t y prime t, and obviously you can just decompose this in a x and y direction, and you can define a velocity. I've definitely seen a question asking for this, and that's just the norm of the velocity vector. So yeah, this velocity doesn't have a direction, it's just a scalar number, but it is the magnitude or norm of the vector. Then the slope, say I go at a point in, let's take this example again, then the slope is actually a y prime of so the velocity vector is y prime t x prime t, but the slope is given by, the slope of this line is given by y prime t divided by x prime t. And then you can also define an acceleration vector, and that for that you take the double derivative of the component. And similarly as the velocity of the moving point, you can define an acceleration, but I'm actually not sure about this. I think it's just the norm of the acceleration vector actually. So which would be then the square root of x double prime t squared plus y double prime t squared. The next page goes over algebraic skills that you definitely need to be aware of. First degree equations, quadratic equations, and power equations. And here you can distinguish even powers. If you have an even power, for example, x to the power n is a, then it will give two solutions with a greater or equal than 0. And one example is, say, x squared is 4, then the two solutions are x is plus or minus the square root of 4, which is plus or minus 2, of course. So two solutions. And a has to be greater or equal than 0. For example, x squared is equal to minus 3, doesn't have any solutions. So that's when n is even. And when n is odd, there's only one solution, a to the power 1 over n. And for example, if x to the power 3 is 8, the solution is just the cube root of 8, which is 2. And if it's negative 64, you get the, any mistakes here. You get the cube root of negative 64, which is minus 4. Then you can get equations with logarithms and exponents. Say you have e to the power x is e to the power 5, then it's just equivalent of saying x equal to 5. And so basically you can safely take the logarithm on both sides. And the same here, if e to the power x is 5, it just means x is the logarithm of 5. And then with trigonometric equations it can be a little bit tricky actually. And they don't work this out here, but I've seen this in several exams, that you have something of the form sine x is the sine of something else, or the cosine is the cosine of something else. And you would easily say, okay, if the sine of x is the sine of a, then it means x should be equal to a. But that's not true for several reasons. One is you have several solutions because these are periodic functions. And then the sines also have several symmetries. And you actually need to work this out, which I wouldn't recommend to do. But I would just remember the solutions. Namely, if the sine of x is sine of a, and you can stop the video to go through this, then you have two solutions, actually many solutions, but kind of two branches. One, it means that x equals to a plus 2n pi with n an integer, or x equals pi minus a plus again 2n times pi. And this one you would easily forget, and probably some points will be discounted. With the cosine, it's similar, but a little bit different. Again, you can do kind of the same derivation. You basically get x is plus or minus a, and then plus 2n pi. And I think I can give an example of that. Let's say something of the form sine x is sine 3x. Again, if you just say x equals 3x, that will be wrong. You have actually many more solutions. So, given what I just mentioned, you have two branches. One, x is equal to 3x plus 2n pi, or x is equal to pi minus 3x plus 2n pi. And if you work this all out, I won't do this here. You can stop the video if you want to look at it. You get these kind of set of solutions, and in particular with this you can have many solutions within a given domain, because it's 1/2 n pi. So this can be 0, can be 1/2 pi, can be pi, etc. And this similar thing for the cosine. So yeah, these are tricky, and I think you could see them in the exams. Then absolute values. It looks simple on paper, it can also be tricky. So basically, if the absolute value of x is a, it means that x is plus or minus a, but also a has to be greater or equal than 0. And, let me see, I worked out an example of that. Let's say we have the equation absolute value x minus 2 is 3x plus 1. Well, that means that either x minus 2 is 3x plus 1, so it's the plus sign here, but also we demand 3x plus 1 is greater or equal to 0. So if you work this out, you get x is 1/4, and if you substitute this in, this is actually satisfied, so this is a solution of these two. Now if I take the minus here, then if I work it out, I get x is minus 3/2, and 3x plus 1 still has to be greater or equal to 0. But if you substitute x here, you actually find that it's not a solution. So we have to discard this. And again, it can become tricky if there are like complicated functions or expressions here. Then finally, inequalities you have to solve by first algebraically calculate the intersections. So, or we're making the sign equal. And after you have done that, you can graphically indicate what the solutions are. Then you need to be able to solve systems of equations by either elimination or substitution. And finally, finding the equation of a straight line. Well, you determine the slope of it, or a normal factor. Well, a normal factor is a factor perpendicular, so I'm not sure how to say this, but you can either determine the slope or the directional factor, and then demand that it goes through a certain point. So anyway, I think we saw this above already, so that should be pretty clear. Some more algebraic skills, page 21. If a times b is 0, it's either a is 0 or b is 0. A squared is b squared means a is either plus of or minus b. A times b equals a times c means either a equals to 0 or b equals to c. And be a little bit careful here. Say you have an equation like this, a times b is a times c. You'll be tempted to divide out a and conclude that means that b equals to c. But that's wrong, because a also can be 0. So you have to include that situation, that a equals 0. Then this is pretty trivial. Now, if you have two fractions that are equal, you can take the so-called cross product, but you have to check that either of the denominators here are not equal to 0. So b times d is not 0, which means that b and d are not 0. So if you see something like this, yes, you can solve this equation, but for every solution you need to make sure that b times d is non-zero. And something like this can be tricky too. Just say you have some complex expression and you take the square, but you had a square root before. You always have to check that what's inside the square root is greater or equal to 0. So again, yes, you can solve a is b squared, but you still have to check your solution later on that a is 0 or positive. Solving equations by substitution, that is, you will see that definitely in the exam, and they give examples here. Where you reduce your equation to equation that you know how to solve. So in both cases you reduce the equation to a quadratic equation. Okay, solving for a variable, applying rules, substitution, anti-derivation. You always need to be aware that the antiderivative or the primitive of a function, you can always add an arbitrary constant to it. Have not seen this often as a problem though. You already learned about the discriminant and how you can use this to find out how many solutions exist if you have a quadratic function. And if you have say you have a quadratic function with a parameter, for example, say a function x minus p squared plus 5, you can write down the discriminant of this with p as a variable, and then you can find for which p something like this has solutions. So yeah, this is actually x squared minus 2p x plus p squared plus 5, and then I just write down my discriminant, b squared. I won't do this now, but you can write down your discriminant and then check for which p this is positive, 0 or negative. Then so you often get these kind of questions with functions that depend on some parameter p. And you just have to consider this like a constant when you take derivatives, etc. But you get questions like, for this kind of class of functions, how to make a curve through the extremes, what they call vertices of the graph. So what you do is you set the derivative of this function 0, and then you get an equation with p. So in this case, if I take the derivative with respect to x, I get that it's 0 when x equal to p. And then if you substitute this back into the function, you get always 5. So for every of these functions, say, I think this is p equal to 0, this is p equal to something, say, larger than 0, say 4, all the vertices are actually on a straight line. And finally, with these kind of examples, they will also say, ask only when does this function touch another function g. And again, you need to, and so touching means that they intersect and have the same derivative. So let's say I have a function g that looks something like this, and that will touch it here. Means that you need to find for which p this function intersects with my function g and has the same slope. So that concludes this video. I hope it turns out to be useful for you. It's actually much longer than I expected. It's a lot of things to prepare, and good luck at your exams.